Okay, this is an introduction to the oscilloscope. This is the oscilloscope we use in ES52. It's a digital 4-channel storage scope. It can measure signals that go up to 200 megahertz, much faster than we're going to need. The purpose of oscilloscope is to allow us to visualize signals that move too fast to measure with our multimeter. Multimeter is great for DC signals, things that don't change, but if they change, the multimeter can't show us anything but numbers. First thing to know is the power switch for our oscilloscope is in the upper left-hand corner. Make sure when you come into the lab you turn it on, because these scopes take quite a while to warm up, and if you need it, you're just going to sit around waiting for it to warm up. So the display on the oscilloscope shows us a picture of time running horizontally and voltage running vertically. In this case, each division, and that's a 1 centimeter division, there's 8 vertical centimeters, is 1 volt. Those are broken up into 5 separate sections, so we've got 0.2 volt, 0.4, 0.6, 0.8 to get 1 volt per division. Horizontally, each division is 500 microseconds. We have a set of controls that allow us to control both the vertical sensitivity, that's the voltage sensitivity, and the horizontal, the time sensitivity, sometimes called the time scale. We also have 4 separate inputs. This scope can display 4 different voltages simultaneously. There's our channel 1 yellow, channel 2 blue, channel 3 pink, channel 4 is green, and that's the colors that appear on the screen. So right now we're looking at channel 1. Now we always want to start with channel 1 if we're looking at only a single signal, and then we can look at other signals using other scopes. So if we want to change the vertical resolution here, we can get the scale, we can go to a more sensitive scale. Instead of 1 volt per division, we're now 500 millivolt per division. That makes our signal bigger, or we can go smaller. Now in general, we don't want to do this. We use visual measurements for the most part on the scope, and if we make the signal small, we're just wasting lots of screen. So we want to use our vertical sensitivity to use as much of the screen as possible. Similarly, if we want to change the horizontal time scale, we use the horizontal time base, and as we change the horizontal time base, we go 250 microseconds per division, 100 microseconds division, 50 microseconds per division. And if it's a repetitive signal, we really don't need to see more than a couple repetitions. So for this signal, 500 millivolts per division and 250 microvolts per division gives us the nicest signal. When you press one of these channel buttons, it does 2 things. If I just press channel 2, it turns on channel 2, and it also changes the list of parameters here to channel 2. If I press channel 1, I get channel 1's parameters. The parameters we care about, coupling. We can switch between DC, AC, ground, go back to DC. In general, we want to use DC. That means what we see on the screen is both the waveform and any DC offset, that's a DC voltage that's added to it. If we move it to AC, we throw out any DC offset. Here we don't have any DC offset, so it looks the same, but the problem with leaving it in the AC mode is if you don't realize it's in the AC mode and you look at a signal that has a DC value, you won't know it. If we press our channel 2 button a second time, we get back our menu. If we press it while our menu for channel 2 is on screen, we turn off channel 2. So we can turn on and off each menu, each channel separately. Bandwidth limit really doesn't affect us much. In general, I would suggest leaving it on. It gets rid of high frequency signals that aren't going to be of interest to us. We don't care about volts per division. Probe should always be in the times 10 position, and our oscilloscope probes have a switch on the side. That switch says times 10 to the left towards the back end and times 1 towards the front end. We want to make sure it's always in times 10. If it's not in times 10, but our scope thinks it's in times 10, the measurements on the scope will be incorrect. Our scope consists of a scope with a probe tib that's spring-loaded. Whoops, I seem to be off screen a little bit. If we pull back the screen, there's a little hook. That hook allows us to hook onto circuit elements. Now, the probe tip comes off to give us a very sharp point which we can use to put into circuit elements to test them. We do not remove our circuit probe tip. The probe tip should always be on. If you need to probe a particular point, you can use the probe to grab a piece of wire and use the other end of the wire to press into the circuit board. So I never want to see a missing scope probe. Our scope also has a ground clip. That ground clip should be connected to 0 volts. If you reverse these, this 0 volt can short out your circuit. This is connected to earth ground. So if you have a circuit that's connected to earth ground and you connect this probe to a voltage, that will cause a short circuit. So the ground clip should only go to ground, and then we can use the scope probe to connect to different points in our circuit to see how they work.